Lecture 10 is Structure and Synthesis of Alkenes. This is chapter 7 from Wade. This is going to be the second major functional group that we're going to dive into. Remember, we started with alkanes, and we said that alkanes weren't really functional because you couldn't do much with them other than burn them or do a free radical halogenation and turn them into alkyl halides. They're not really considered a functional group. Alkyl halides certainly considered a functional group because we can put a halogen on an alkane and then eliminate it with E1 or E2. We can substitute it with E1 or E2. So alkenes then, we know how to make them from E1 or E2. So chapter 7 in Wade dives into the world of alkenes, which is the IUPAC name for double bonds. In Wade, the textbook that we're following, the method of organization is as follows. Basically, the entire book is a tour of functional groups. You start with alkanes, then haloalkanes, then alkenes, then alkynes, then alcohols, then ethers, then carboxylic acids and derivatives, and et cetera, et cetera, et cetera. Every time you cover a new functional group in Wade, they kind of divide it into two parts. The first part is structure and synthesis. So you look at the orbitals, the structure, the way that things are bonded, maybe their conformational dynamics, how they bend or twist or rotate, and also synthesis. So how to make the functional group, which with alkenes, we kind of already know that. There are a couple other ways to do it besides from E1 or E2. And then the second part of the functional group chapter will be reactions of alkenes. So we have synthesis of the functional group, meaning how do we make it? And then reactions of the functional group, meaning how can we use them to make other functional groups? So we're going to spend one lecture, lecture 10, on structure and synthesis of alkenes, and then lectures 11 and 12 are going to be the reactions of alkenes. There are a lot of reactions of alkenes. They're very specific reactions that do very specific things, and it's just not feasible to cover it in one lecture. So we're going to divide that into two lectures. Now, this is actually a good point to issue a warning that this is really the first time in this class that we're really going to get inundated with reactions. So we have learned free radical halogenation. We learned E1 and E2, SN1 and SN2. Those were general classes of reactions. But in the reactions and synthesis of alkenes, we're going to cover maybe 10, 12, maybe 14 very specific reactions, all for alkenes. So we might learn anywhere from 10 to 20 reactions for every functional group, and we're going to cover anywhere from, say, 15 to 20 functional groups. So we're going to be looking at a lot of reactions from here on in. And so this is a warning to not fall behind. Make sure that you keep up with your organization. If you're making flashcards, it's good to make flashcards. Keep doing that. Whatever you're doing to keep your information organized, this is a good time to perfect that method. So like I mentioned, alkenes are the functional group name that we give to a double bond. So alkenes are hydrocarbons that contain at least one carbon-carbon double bond. Remember that alkanes, we said, were hydrocarbons that were all single bonds. So now alkenes, we're adding in a double bond. Sometimes alkenes are called olefins. That word is derived from a gas called olefiant gas, which there was a reaction that you could perform on olefiant gas that would turn the gas into an oil. And this is also reference to the oily appearance of many alkenes and alkene derivatives. Alkenes are among the most important industrial compounds. They are used for lots and lots and lots of things, and especially like plastics and polymers and materials. They are very versatile from a synthetic perspective. You can turn alkenes into lots of other things. We're going to see we can turn them into alcohols. We can turn them back into halogens. We can turn them into triple bonds. We can turn them into single bonds. We can turn them into amines and ketones and aldehydes. We can turn them into all kinds of different things. And we can have reactions that act very specifically with regards to stereochemistry. We can get anti configurations or syn configurations. They're very, very versatile. And because of that, there's lots of reactions that we have to learn with them. Let's look at the double bond really quick. The dissociation energy of a double bond, meaning the amount of energy that you have to put into a molecule to break its double bond, is 611 kilojoules per mole. We know that the single bond, the sigma bond, dissociation energy is about 347 kilojoules per mole, which means that if you subtract off the sigma bond energy from the overall double bond energy, you are left with the pi bond dissociation energy, which is 264 kilojoules per mole. Now, that is less energy than a sigma bond, meaning that it requires less energy to break it, which means it's weaker. So the pi bond is weaker than the sigma bond and is therefore more reactive. Sometimes a term that's used for that is labile. We say that a functional group, or in this case, the double bond, is labile. It is able to be transformed. It is also indeed functional, like we said. We can exploit the pi bond's reactivity to do some very interesting chemistry. So we already know how to make them. We talked about E1 and E2 in the previous lecture. And ideally, we'd like to know what we can do with them. And that's going to be, like I said, lectures 11 and 12. So let's spend a little bit more time looking at the double bond. Remember that a double bond is formed when you have two unhybridized p orbitals that are adjacent and parallel to each other, overlapping with side-to-side overlap. Here we've got two sp2 hybridized carbons. So one carbon with its three sp2 orbitals, another carbon with its three sp2 orbitals. In this case, we have two of those sp2 orbitals on each carbon simply overlapping with hydrogens. The other sp2 orbitals are overlapping with each other. That's the sigma bond. Then the pi bond is both above the plane of the sigma bond and below the plane of the sigma bond. The side-to-side overlap of the p orbitals is the pi bond, and we count this as half and this as half. That's actually very important. You can look at the molecule this way. Again, here's our picture of our p orbitals overlapping. In this case, they're just showing both of the electrons in the upper lobe. They can also be in the lower lobe. There's some quantum mechanics there. They can be both places at the same time. In the balloon picture, it kind of looks like this. They like to show the balloons kind of smeared into one another to show the bond. Another way you can look at it is like this sandwich. This is really nice because it shows how the atoms in the sp2 carbons are all flat. They're all planar. They're kind of sitting in a plane. And then we have these disks of electron density above the plane of the molecule and below the plane of the molecule. If you look at an electron potential map of a simple alkene, you can see where all the pi density is. All of the electron density is above the plane of the molecule and below the plane of the molecule. And again, like I said, this is important because that means that you can have an electrophile approach from either the top face of the alkene or the bottom face of the alkene. Maybe one face is preferred over the other, maybe neither face is preferred over the other one. That will play a role in the stereochemistry of the products and the way, the kind of the pathway that the reaction takes. Remember that you cannot rotate freely around a double bond. The mere existence of a double bond is due to or relies on these p orbitals being parallel to each other. And if you try to rotate this sigma bond, it would force these p orbitals, say we hold the left carbon the same and rotate the right carbon, it's going to force the p orbitals on the right carbon to be perpendicular to the p orbital on the left carbon. And that would break the bond. So if you rotate that, you get no overlap if they're perpendicular. And so we're not allowed to rotate. We can't go from a Z double bond or say a cis double bond to a trans double bond by rotating around that. It turns out that, like we said, the dissociation energy for a pi bond is about 250 kilojoules per mole. That's only a little bit weaker than the dissociation energy of a sigma bond. And we certainly wouldn't just allow ourselves to snap a sigma bond in half, just break a molecule apart just by rotating it. That's not going to happen. So rotation would break the bond, but that would require way too much energy, so it just doesn't happen. Double bonds belong to a group of functional groups that we call elements or indexes of unsaturation. The term saturation or unsaturation means something very specific in chemistry. Saturation means basically that there are as many hydrogens as possible given the number of carbons present. So that's saturation. An example of a saturated molecule would be a linear alkane. For example, here's butane, a linear alkane. And if we look at butane, we've got 4 carbons and we have 10 hydrogens. Basically, every slot that is not taken up by one of the carbon bonds is taken up by a hydrogen bond. So we've got as many hydrogens as we can fit on this molecule, given the fact that we've got 4 carbons. Obviously, if we had 5 carbons, we'd have more room for more hydrogens. Or if we had 3 carbons, we'd have fewer slots for those hydrogens. But given the fact that we've got 4 carbons, the way that those 4 carbons attached in this linear fashion means that we can fit 10 hydrogens, as many as 10 hydrogens around those carbons. That is what we mean by saturation. So linear alkanes are saturated. So unsaturated then simply means that there are fewer than the maximum number of hydrogens that we could have given the number of carbons. So remember that for an alkane, a linear alkane, we said that the formula was CnH2n plus 2. That way, if we have 4 carbons, we have 2 times 4 plus 2 equals 10 hydrogens. That's a saturated alkane. That's the formula for a saturated alkane. For unsaturation, I'm going to modify that formula a little bit. It's going to be CnH2n plus 2 minus 2x, where x is an index of unsaturation, some element, some structural element. I don't mean a chemical element. I don't mean like, bromine is an element or argon is an element. I mean some structural feature, some structural element of the molecule is X, the index of unsaturation. Essentially, if you look at this formula, an element of unsaturation is any structural feature that reduces the number of hydrogens by 2, increases X. If we have one element of unsaturation, our X is 1, we're going to subtract 2 hydrogens from our formula. If our X is 2, we're going to subtract 4 hydrogens from our formula. So we can look at any formula and figure out, based on the number of hydrogens relative to the number of carbons, how many elements of unsaturation do we have. For example, let's look at butene. This is butene. We're going to talk about naming alkenes in a little bit. But here's butene. It's 4 carbons. And how many hydrogens? Well, it's only 8 hydrogens. We've got 3 on the ends, just like we had in butane, 3 on the ends. But since the 2 middle carbons have a double bond, each one has 1 less slot available for a hydrogen. Carbon 2 and carbon 3 only have 1 hydrogen on them, whereas carbon 2 and carbon 3 have 2 hydrogens on each other in butane. So compare the formulas. With butane, it was C4H10. For butene, it was C4H8, meaning that given the fact that we've got 4 carbons, the maximum we could have would be 10. We have 8, so we are missing 2. So since we have decreased the number of hydrogens by 2, that means we have 1 element of unsaturation. And that element of unsaturation is the double bond. The double bond is responsible for taking up the space of 2 hydrogens. So we have to lose 2 hydrogens from our structure in order to allow for the presence of the double bond. Let's look at some other elements of unsaturation. Here's a triple bond. Here's butane. We'll talk about naming triple bonds when we talk about alkynes in a couple chapters. But again, we've got 4 carbons, 1, 2, 3, 4, where the 2 middle carbons, carbon 2 and carbon 3, are triple bonded. So if we look at the number of hydrogens there, we've got 3 on the ends, on each of the ends, but the carbons that are triple bonded don't have any room for hydrogens on them. All of their 4 bonds are being taken up. So what's our formula? Our formula is C4H6. So rather than having C4H10, we are missing 4 hydrogens, which means that we have now 2 indexes of unsaturation. And those elements of unsaturation are the 2 pi bonds. Remember, the first pi bond, we lost 2 hydrogens. If we add a second pi bond, we lose another 2 hydrogens. Let's keep going. Let's look at some other examples of saturated and unsaturated molecules. Here's hexane. 6 carbons, 1, 2, 3, 4, 5, 6, all single bonds. Its formula is C6H14. That is CnH2n plus 2. So this is a saturated structure. We have as many hydrogens as we can fit on the fact that we've got 6 carbons. That makes 14. Let's look at this structure. Now you notice that we've got 2 double bonds here, which means that if this is consistent with what we saw on the previous couple slides, we should have 2 elements of unsaturation. Each double bond, each pi bond, I should say, is an element of unsaturation. What's the formula? The formula is C6H10. That is, we are missing 4 hydrogens, or 2 degrees of unsaturation. Each degree of unsaturation reduces the number of hydrogens by 2. So those 2 indexes of unsaturation are the 2 pi bonds. How about cyclohexane? Here we go. So again, the formula for cyclohexane, C6H12, meaning that we've got 6 carbons, but we don't have as many hydrogens as we can fit. We don't have 14. Instead, we have 12. So that means that we've lost 2 hydrogens from our maximum amount possible, which means that our index of unsaturation is 1. What structural element in this molecule is the element of unsaturation? Can you tell? It's the ring. Think about it. In the linear form, all of these middle carbons, 1, 2, 3, 4, those 4 middle carbons all have 2 hydrogens. That's fine. But the end carbons, that one there and that one there, each of those end carbons has 3. So if we look at the ring, we don't have any end carbons. Every single carbon in our 6-carbon ring only has 2 hydrogens. So we are essentially losing 1 hydrogen from each of the ends in the linear structure in order to make the ring. In order to connect those 2 ends to one another, each one needs to lose a hydrogen. So a ring can be an element of unsaturation. Just to go back and remind ourselves, a pi bond could be an element of unsaturation. 2 pi bonds in an alkyne would be 2 elements of unsaturation. Or 2 bonds in a diene, a double alkene, would be 2 elements of unsaturation. A ring could be 1 element of unsaturation. How about this guy? Here we've got another structure. What are our elements of unsaturation? We've still got a ring, so that's 1. The ring should remove 2 hydrogens from our structure, from our saturated structure, and the double bond should remove 2 hydrogens from our saturated structure. So the formula is C6H10. That's minus 4 hydrogens from our saturated structure. So indeed, we have 2 elements of unsaturation, the ring and the double bond. Let's look at some other functional groups and see how they affect the degree of unsaturation for a structure. For halogens, we count them like H's. Since halogens only make 1 bond and H's only make one bond, that doesn't change the amount of unsaturation on the molecule. Technically, yes, having a halogen removes a hydrogen, but remember we said that an element of unsaturation should remove two hydrogens. Every X we had removed two. So since they bond like hydrogens, we're just going to ignore them. So C6H13Br, which is this formula for this structure, if we're going to treat the halogen like a hydrogen, that might as well be C6H14. And again, that means that our X is 0. This does not count as an element of unsaturation. Oxygens are a little weird because it depends on other contexts, whether or not they saturate or unsaturate the molecule. If you take a normal alkane and you put an oxygen in place of a hydrogen, you end up with another hydrogen on that oxygen. If you put an OH group on a molecule, you don't affect the overall number of hydrogens that are there. This structure is C6H14O, which means compared to normal hexane, which was C6H14, this does not lose any hydrogens. This might as well be C6H14, which means our X is 0. So we ignore single bonded oxygens, OH groups. Those do not affect the degree of unsaturation of a molecule. You still end up with the same number of hydrogens on our 6-carbon chain, or on our molecule with a 6-carbon chain, whether we had the O there or not. But a double bonded oxygen does. A double bonded oxygen does affect the overall number of hydrogens on the molecule. So this structure is C6H12O. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So C6H12O looks like C6H12, right? We are missing 2 hydrogens given the fact that we should have 14 on 6 carbons. So that double bonded oxygen removes 2 hydrogens from our structure. It therefore counts as a degree of unsaturation. Double bonded oxygens do count. We treat double bonded oxygens just like double bonded carbons did. They were 1 degree of unsaturation. Let's look at this molecule here. This is called THF, tetrahydrofuran. I believe we used it as a polar aprotic solvent when we looked at SN2 reactions. What's the formula? The formula is C4H8O. Now, if we have 4 carbons, the maximum number of hydrogens that we could have would be 10. We saw that with butane. Butane was C4H10. This is C4H8O, which means that we have lost 2 hydrogens. Now, what is the structural element that caused us to lose 2 hydrogens? Remember, it's not the oxygen. We said that single bonded oxygens do not affect the amount of hydrogens that we have. So it's not the oxygen that's losing 2 hydrogens here. What it is the ring. We've got a ring structure, and we saw that rings reduce the number of hydrogens by 2 because our end atoms, usually they're carbons, our end atoms are now attached to one another. So we are ignoring the single bonded oxygen here. The element of unsaturation is the ring. What about nitrogens, though? Nitrogens are kind of interesting. They're kind of weird. They're definitely the most tricky. Here's our similar structure with nitrogen. Looks like our ring, our 4-carbon ring with oxygen, but we've got a 4-carbon ring with nitrogen. Remember, nitrogen gets an extra bond. Nitrogen gets 1 more bond than oxygen does. And in this case, for this structure, that bond is being formed to a hydrogen. So what's our formula? It's C4H9N. So how does this work? Well, we're going to count nitrogen like half of a carbon, meaning that we're going to treat this molecule as if it has 4.5 nitrogens. If this has 4.5 carbons, what's the maximum number of hydrogens that we could have? Remember, it's 2 times the number of carbons plus 2. So 2 2 times the number of carbons would be 9, plus 2 would be 11. So given 4 carbons and a nitrogen, the maximum number of hydrogens that we could have would be 11. 4.5 times 2 plus 2. This is not 11, this is 9, which means that we have one element of unsaturation. We have some structural feature that has caused us to have 9 hydrogens instead of 11. What is that structural feature? It's the ring. So nitrogens, nothing too fancy. We just treat them like half of a carbon would in the normal CnH2n plus 2 formula. And again, rings count as elements of unsaturation. If we combine everything that we've just shown into this formula here, we could calculate elements of unsaturation directly. This says we take 2 times the number of carbons in our formula, plus 2, so 2 plus 2 times the number of carbons. We're going to subtract off the number of hydrogens and halogens, X's are halogens, subtract off the number of hydrogens and halogens, and then we're going to add the number of nitrogens in our formula. Notice that, remember, we treated nitrogen like half of a carbon, so instead of having 2 times the number of carbon, we just have 1 times the number of nitrogen, and then we divide it by 2, because the number of hydrogens is 2 plus the number of carbons times 2, right? 2n plus 2. So use this formula, memorize this formula. The number of carbons in your structure, the number of hydrogens in your structure, the number of X's in your structure, the number of nitrogens in your structure. 2 plus 2 times the number of carbons minus H plus X plus N divided by 2 will give you your element of unsaturation. If you want, go back and apply this formula to any of these other molecular formulas that we said, C6H12O, C4H8O, C4H9N, any of these other formulas that we looked at, plug them into this equation, and you will get the number of elements of unsaturation. This is the most math that you're ever going to have to do in organic chemistry. Okay, let's talk about nomenclature of alkenes. Talk about how alkenes are named. We spent a good amount of time looking at alkanes, single bonds, and alkenes are really not that much different than alkanes in the way that they are named. Simple alkenes are named much like regular alkanes. We're going to use the root name of the longest chain containing the double bond. That's pretty important. Usually the double bond is treated as being part of the main chain. There are some exceptions, sometimes when we use a double bond as a substituent, when it just simply makes more sense to not have it be part of the main chain. But usually we're going to designate the main chain as the chain containing the double bond. The ending is changed from ane to ene. I've used that a lot. We're talking about alkenes instead of alkanes. So a 2-carbon alkane was ethane. A 2-carbon alkene is ethene. A 3-carbon alkane was propane. A 3-carbon alkene is propene. A 6-membered ring with all single bonds was cyclohexane. If we have a 6-membered ring where there is a double bond, it's cyclohexene. So here's ethene, here's propene, and here's cyclohexene. Now, anytime that the chain contains more than 3 carbons, you need to designate where the double bond is. So we're going to use a number to give the location of the double bond, meaning essentially the carbon that the double bond starts on. The chain is always numbered starting from the end closest to the double bond, and you number through the alkene. And cycloalkenes are always assumed to have the double bond in the number 1 position. So here's a 4-carbon chain. So that would be butene. But for 4 carbons, there's a double bond, so it's butene. But notice that we could have 2 different kinds of butene. We can have butene with the double bond between carbon 1 and carbon 2, or you could have the double bond between carbon 2 and carbon 3. That's two different possibilities. These are constitutional isomers. Just by the way, notice that having the double bond between 3 and 4 is the same as having the double bond between 1 and 2. So we would always number it from the end closest to the double bond. So 1 butene means we've got a 4-carbon chain with a double bond on the 1 carbon from 1 to 2. 2 butene means we've got a 4-carbon chain with a double bond starting on the 2 carbon from 2 carbon to 3 carbon. Here's a 5-carbon chain. So that's pent. Pent is our root. We've got a double bond, so that's pentene. And the double bond starts on the 1st carbon. So that's 1 pentene. Here's, again, a 5-carbon chain, so pent with a double bond, so it's pentene. The double bond starts on the 2 carbon, goes from carbon 2 to carbon 3, so it's 2 pentene. Here, notice the way that we numbered it. We numbered it from left to right so that we got the double bond on the 2 carbon. If we were to number this from right to left, we would get to the double bond on the 3 carbon. So we would number it from the side that gives the lowest number to the alkene. The chain is numbered from the end closest to the double bond. And we always number through the alkene. By through the alkene, what I mean is for cyclohexene, we number it this way so that we go carbon 1, carbon 2 involving the double bond. We wouldn't start on carbon 1 and then go away from it. So we wouldn't go carbon 1, carbon 2, carbon 3, carbon 4. We're always going to number through the double bond. So that's cyclohexene. Now, why wouldn't we put a 1 here? Why wouldn't we call this 1 cyclohexene? Well, because for cyclohexene, by definition, the double bond is always going to be on the 1 carbon. So we could put 1 cyclohexene here, but it's redundant. So usually it's just left off. I won't mark it wrong if you say 1 cyclohexene because I clearly understand the structure that you're communicating. But if you leave off the 1, I also won't mark you wrong. That would be absolutely acceptable. Now, about, I think 30 years ago or so, IUPAC, the International Union of Pure and Applied Chemistry, recategorized or reformulated the way that alkenes are named. So there's a new way to do alkenes and an old way to do alkenes. And still today, even though this was about 20 or 30 years ago, both naming systems are used kind of interchangeably. So here's what we do. In the old naming system, notice that we put the number indicating the location of the double bond. We append that to the beginning of the name. 1 butene, 2 butene, 1 pentene, 2 pentene. In the new naming system, we split the root. So we split the but and the ene, and we put the 1 in between it. Now, why do we do that? It actually is a lot more logical because now the 1, the number that indicates the position of the alkene, directly precedes the ene. Remember when we were naming alkanes, we had something like 3-bromo or 4-isopropyl or 2-methyl or 3-methyl or 2,2,6-trimethyl. In the naming system for alkanes, you always preceded the functional group with the number carbon that it's on. So in this case, we're doing the same thing. We're preceding the number with the functional group that it's on. So but-1-ene or pent-1-ene or but-2-ene or pent-2-ene. This might seem awkward, but when we get to more complicated structures, it's much, much, much more clear to name it with the new system than the old system. I personally don't care which one you use. I understand both systems just fine. Any organic chemist would understand both systems just fine. So choose whichever one you like and use it consistently. Just make sure you do it correctly. That's all I care about. Now, many alkenes have more than 1 double bond. So in the event that our structure has multiple double bonds, here's how we deal with it. A compound with 2 double bonds, we call a diene. With 3 double bonds, we call it a triene. 4 double bonds, we call it a tetraene, etc., etc., etc. And this probably didn't surprise you. Numbers are used to specify the locations of each double bond. So here's a molecule with 2 double bonds. This is a diene. It's a 4-carbon chain, so it's butadiene. Now, butadiene is kind of awkward to say. So when sometimes you will put an A between that. So instead of butadiene, it's butadiene. That's a lot easier to say. If you say butadiene, I probably wouldn't care. That's probably fine. Most people would understand what you're saying. But buta is more easy to say than but. So that's fine. So this is 1,3-butadiene. We have a carbon double bond between 1 and 2 and between 3 and 4. That's what the 1 and the 3 reference. Now again, this is the old naming system because we are prepending the numbers to the name. In the new system, we would split the root again. We're going to put the numbers directly before the functional group that they reference. So buta-1,3-diene means it's a 4-carbon chain with a 1-ene and a 3-ene. Here's a 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. Our double bonds start on the 1, goes to the 2, starts on the 3, goes to the 4, and starts on the 5, goes to the 6. Notice that we number it from right to left because that gives us the double bonds on the 1, the 3, and the 5. If we were to number it from left to right, we would have our double bonds on the 2, the 4, and the 6. So we're going to choose our numbering system so that it gives us the lowest numbers possible on the alkenes. So 7-carbon chain would be heptatriene. 7 carbons would be hept. 3 double bonds would be a triene. You could say heptatriene, but that's pretty awkward. So you just say heptatriene. And those double bonds are on the 1, the 3, and the 5. So it's 1,3,5-heptatriene. Or the new system, if you want to split the root, hepta-1,3,5-triene. The last one's my favorite, and I know we used this structure before when we were looking at aromaticity and anti-aromaticity. Here's an 8-carbon ring, and it's got 4 double bonds. So if this was just an alkane, it would be cyclooctane. But we have double bonds, and we've got 4 of them. So it's cyclooctatetraene. It's a really fun thing to say, cyclooctatetraene. And where are our double bonds? We have double bonds from the 1 to the 2, from the 3 to the 4, from the 5 to the 6, and from the 7 to the 8. Remember that in cyclic structures, you're always going to start an alkene on the 1, and you're going to number through it. So we go from 1 through to 2, from 3 through to 4, from 5 through to 6, and from 7 through to 8. So this is 1,3,5,7 cyclooctatetraene. It's kind of fun to say. It's less fun to split the root. Cycloocta-1,3,5,7 tetraene does not sound nearly as cool as 1,3,5,7 cyclooctatetraene. But there you go. That's how you do alkenes with multiple double bonds. Or let's get a little bit more sophisticated. Let's look at alkenes with substituents. Here we're going to look at alkenes that have substituents. We're just going to use alkyl substituents for the moment. Methyl, ethyl, propyl, etc. In this event, the alkene gets the priority over the alkyl substituent when we name something. Let me show you what I mean by that. Look at this structure here. What's our longest carbon chain? It's 4 carbons. 1, 2, 3, 4. Or we could go this way, 1, 2, 3, 4. But no matter how you number this molecule, as long as you go through the double bond, you always have 4 carbons as your main chain. If we number from 1 through 4, where are the substituents and where is the double bond? Well, clearly we have a methyl substituent on carbon 2, and the double bond starts on carbon number 2. So we would call this 2-methyl 2-butene, or 2-methyl butene, depending on whether you want to use the old-fashioned system or the new system where we split the root. 2-methyl-butene. Now, in this case, there's no argument as to where the methyl goes and where the double bond goes. They clearly go on the 2-carbon in either case. But sometimes you might have a difference in opinion. For example, if we number this molecule from right to left, the double bond goes on the 1, so 1 to 2. That puts the substituent, the methyl, on the 3. If we number the other direction, it puts the methyl on the 2 and the double bond on the 3 if we go left to right. So we are going to number this molecule and therefore name it in such a way that the alkene gets the priority. We're going to number to favor the alkene over the alkyl substituent. So we're going to number it right to left so that the alkene gets the 1 and then the methyl gets the 3. So this is going to be 3-methyl, 1-butene, or 3-methyl-but-1-ene. This should actually be 3-methyl-but. There we go. 3-methyl-but-1-ene. All right. How about this guy? What's our longest carbon chain? Well, they've got it numbered here. It's 7 carbons. 1, 2, 3, 4, 5, 6, 7. Looking at this structure, they have numbered it from left to right so that the double bond goes on the 2 and everything else gets, say the methyl gets on the 3, the other methyl gets on the 6. If we were to number it in the other direction, we would have a methyl on the 2, a methyl on the 5, and the alkene on the 5. That would be giving preference to our methyl substituents over our alkene. But the rule again is that the alkene gets priority. So we're going to number it to get the lowest number possible on the alkene and let everything else fall where it may. So 7-carbon chain with a double bond means that this is heptene. Specifically, it's a 2-heptene or hept2ene. What else do we have? We have methyls on the 3 and methyls on the 6. So we have 3,6-dimethyl 2-heptene or 3,6-dimethyl hept2ene. This last molecule down here, we would number it this way. We're going to number it so that the longest chain involves our double bonds. So that's going to be the 6-membered ring is the longest chain. So we're going to number it so that our alkene gets priority. So we're going to number it 1 to 2 to 3 to 4. Now, here's a question. If we number it this way, like I drew it, 1 to 2 to 3 to 4, our alkenes are on the 1 and the 3. And our ethyl is on the 2. If we number it the other direction, if we say start here on the 4 and we go 1 to 2 to 3 to 4, our alkenes are still 1 and 3. Whether we start numbering on the left over here or on the right over here, we always have the alkenes on the 1 and the 3. But if we start on the left, our ethyl gets a 2. If we start on the right, our ethyl gets a 3. So in the event that the numbering system does not affect the alkene, and it's the same either way, then we're going to prioritize our numbering so that our alkyl group, our substituent, gets the lowest numbers. So what do we have? This is a cyclohexadiene. It's a 6-carbon ring with 2 double bonds. So cyclohexadiene, those double bonds are on the 1 and the 3. So it would be a 1,3 cyclohexadiene. And then we have an ethyl group, a 2-carbon substituent, 1, 2, on the 2-carbon. So 2-ethyl, 1,3 cyclohexadiene would be the old naming system, or 2-ethyl cyclohexa 1,3-diene in the new naming system when we split the root. We can do more naming practice in workshop if you so please. Here are some examples of structural elements where it makes sense to name an alkene as a substituent rather than as being part of the main chain. For example, look at this structure here. Notice that we've got a 6-membered ring with a double bond on it. So this is a cyclohexene ring. But what is this? This is a double bond sticking off of the ring, almost like it's a substituent. That group, a double bond CH2 group, is called methylene. Sometimes it's called methylidine. That's the kind of older naming system for it. But we call this methylene. So this would be a cyclohexane, where we number, again, starting in the ring, our double bond is always going to be number 1. So 1, 2, 3. So cyclohexene with a 3-methylene. 3-methylene cyclohexene. Again, where's the 1? Why don't we have a 1 here? Because it's assumed that in our ring, the double bond starts on the 1 carbon, and then our methylene group would be on the 3. That's a methylene group. This is a vinyl group, a C double bond C coming off the main chain. Not just a double bond C, but a C double bond C coming off the main chain. For example, this structure here. Here we've got a 1, 2, 3, 4, 5, 6 carbon chain, and then we've got this thing coming off of that chain. We can't include this as the main chain. We can't go 1, 2, 3, 4, 5, 6. Well, then we have it coming off over here. Or we go 1, 2, 3, 4, 5 is not as long of a chain. So whether we go 1, 2, 3, 4, 5, 6, then we have this same group coming off on the left, or we go 1, 2, 3, 4, 5, 6. We have this blue group coming off at the top. That's a vinyl group. So this is a 6-carbon chain with 2 double bonds on it. So it's a hexadiene. Those double bonds are on the 1 to 2 and the 5 to the 6. So that's a 1,5-hexadiene with a vinyl group on the 3rd carbon. So 3-vinyl 1,5-hexadiene, or 3-vinyl hexa 1,5-diene. Again, if you want to split the root. It's a vinyl group. Here's an allyl group. Again, it's kind of like vinyl, but we've got 1 more carbon between the double bond and the main chain. Remember we talked about the allylic position? This carbon right here being adjacent to a double bond, that is the allylic position. And in this example, the allylic position is the position that's attached to the main chain. So imagine that you've got like a 100-carbon chain, and then you've got this little group popping off of it. That would be an allyl group off of our 100-carbon chain. It makes more sense to name this as a substituent if it's, say, coming off of a very, very, very large chain than it does to try to incorporate it as the main chain and name the other giant pieces as substituent. That's an allyl group. This is phenyl group. Basically, this is a benzene ring as a substituent, is a phenyl group. Sometimes it makes sense to name phenyl as a substituent rather than to make it the main chain. Again, imagine we've got a 100-carbon chain with this little ring coming off of it. It makes more sense to name that as a 100-carbon chain with a phenyl group coming off of it than name the ring as a benzene with a 100-carbon chain coming off of it. So that's phenyl, and we abbreviate it PH. Be aware there's another functional group called phenol, PHENOL. That's phenol. That's a very different molecule than phenyl. So just be aware of that. Just if you're going to say phenyl, make sure you don't pronounce it phenol. Or if you're going to say phenol, make sure you don't pronounce it phenyl. And that's abbreviated pH. Here's an example. Here's a 5-membered ring. This is cyclopentadiene. Again, it's a 5-carbon ring, so it's a cyclopent, but it's got 2 double bonds in it, so it's cyclopentadiene. If we were to number those double bonds, they would be on the 1 to the 2 and the 3 to the 4. So that's a 1,3 cyclopentadiene. And then we've got this ring coming off of it, this benzene ring that's a substituent. So we could call it 2-phenyl. It's got a phenyl group coming off of the 2-carbon of the cyclopentadiene. Here's allyl chloride. It's an allyl group, allyl coming off of chlorine. Allyl chloride. You could also name this as 3-chloropropene. Think about that. It's a 3-carbon chain with a double bond. So it's propene. And we would number this with the 1 on the double bond. So 1, 2, 3. It's a 1-propene. Again, because there's only 3 carbons, the double bond's always going to be on the 1 carbon. And the chlorine is then going to be on the 3. So 3-chloro-1-propene. Just as a quick reminder that in double bonds, we have the opportunity to have geometric isomers. Since we cannot rotate around that double bond, we have 2 potential configurations of that double bond, and we call one of them E and the other one Z. Just to remember that, we rank the groups on each carbon by which one has a higher stereochemical priority: bromine over chlorine on the left carbon, methyl over hydrogen on the right carbon. Since the ones are together, they're on the same side of the double bond, that's a Z. If we flip that around, we're going to keep the right carbon the same, and we're going to change the left carbon. Again, note, we're not rotating. We did not rotate this double bond. You're not allowed to rotate the double bond. Rather, we have just removed these atoms and reconnected them. So these are different molecules. They're not the same. They're not the same, just rotated. They're literally different ones. Now the bromine, the 1, and the methyl, the 1, are on opposite sides of that double bond. So if they're opposite sides, we call it E. And we prepend the stereochemical designation to the beginning of the name, and we usually put it in parentheses. So this is not just 1-bromo, 1-chloropropene. Here's a 3-carbon chain, 1, 2, 3. We'd start from the end closest to the double bond, so we would number it 1, 2, 3. That's propene. And we've got a bromine on the 1 and a chlorine on the 1. So 1-bromo, 1-chloropropene. But this is also 1-bromo, 1-chloropropene. You see that? We still got a chlorine and the bromine on the first carbon, but they are in different positions on that 1 carbon. And so we have to say whether they are in the Z position relative to the methyl or the E position relative to the methyl. Here the bromine, the larger group, is opposite of the larger methyl on the other side. So that's E. Here the bromine is on the same side of the larger methyl. So that's Z. Also a reminder that alkenes increase in stability as they become more substituted, meaning as they have more carbon groups on them. Here's a double bond with no carbon groups on them, only hydrogens. We call that unsubstituted, and they release, this molecule releases 32 kcals per mole, nearly 33 kcals per mole, when you hydrogenate that, when you remove the double bond. Here, this is a mono-substituted because we have one group, this ethyl group, coming off the double bond. That only releases 30.3 kcals when we hydrogenate it, when we get rid of that double bond. So it released less energy, meaning there was less energy in that double bond, meaning it's more stable. Here we have a di-substituted, where one carbon on one double bonded carbon and another one carbon on the other double bonded carbon. So 2 carbon substituents, di-substituted. That only releases 27.6 kcals per mole. Again, less energy is released than these other ones, which means there was less energy in it, which means it was more stable. Tri-substituted releases even less energy, and tetra-substituted releases even less energy. So we increase stability as we increase substitution. And that is why Sitzeff's rule is a rule. Sitzeff's rule says that when you do an elimination in E1 or E2, you always preferentially form the double bond that is more substituted. If you have the choice of making a mono versus a di, you'll make the di. If you have an option of making a di versus a tetra, you'll make a tetra, etc. This is not necessarily related to alkenes, but they are related to the idea of elements of unsaturation. Remember, we saw that double bonds or pi bonds count as elements of unsaturation, and rings count as elements of unsaturation. So I'm going to show you some examples of bicyclic molecules, molecules that have two rings in them, because there's a separate naming system for bicyclic molecules than we use for other normal cyclic molecules or linear molecules. There are three types of bicyclic molecules. You can have fused bicyclic, which are basically two rings that are fused together, two rings that share a bond, like that. That's a fused bicyclic. You can have a bridged bicyclic molecule, which is where you have two rings where one of the ring bridges the other one. You can look at this as a 5-membered ring and a 6-membered ring. Where's the 6-membered ring? Here's the 6-membered ring. 1, 2, 3, 4, 5, 6, and then back to 1. So the 6-membered ring is along the bottom, kind of the base of this structure. But look here, there's a 5-membered ring. 1, 2, 3, 4, 5. There's a 5-membered ring that bridges the 6-membered ring. That's a bridged bicyclic. And we call these carbons right here bridgehead carbons. They are the carbons that have the bridge on them. This is called spirocyclic. Notice that in the fused bicyclic and bridged bicyclic, the two rings share two carbons. Here, the left ring and the right ring share these two carbons right here. 1, 2. Here, the 6-membered ring and the 5-membered ring share the bridgehead carbons, two carbons there. In the spirocyclic bicyclic molecule, they only share one carbon. Notice the interesting geometry in the spirocyclic molecule. One ring, let's say the left ring, you can see that it's kind of flat in the plane of the board, and the ring on the right is perpendicular to the plane of the board. These rings sit at 90-degree angles from one another, or nearly 90-degree angles from one another. That's because this central carbon, the carbon that shares the ring, that's a tetrahedral carbon. So two molecules in the left ring have to be at 109.5 from the two carbons in the right ring. That's spirocyclic. Let's look how these are named. Let's start with the bicyclic molecule first. Ignore what's in parentheses. The parentheses names are common names. And like I said, most molecules have a common name along with their IUPAC name. And I don't want you to worry about learning those. You might come to learn them just from experience, from being exposed to them a lot, but I don't want you to memorize them. So let's look at this bridged bicyclic molecule, and let's look at the name, and let's see if we can figure out the pattern. First of all, let's start with the root. It's heptane. That means that there are 7 carbons, and they're all single bonds. Heptane. That is what we have here. Where are our 7 carbons? There's the 6 carbons in the ring. Remember, 1, 2, 3, 4, 5, 6. And then we have a 7th carbon in the bridge. This 1 carbon bridge gives us our 7th carbon. So what does the 2.2.1 in brackets mean? Well, here's what it means. The 2, or both 2's in this case, refer to how many carbons are on each side of the bridgeheads. So here are our bridgeheads. We have 2 carbons on one side, right there and right there. We have 2 carbons on the other side, right there and right there. So 2 on one side, 2 on the other side, and then the last number is the single carbon in the bridge. It's a 1 carbon bridge. So 2.2.1 heptane means we've got 2 carbons on one side of a bridge, 2 carbons on the other side of the bridge. We've got 1 carbon between the bridge. Notice that the sum of these numbers, 2.2.1, is 5, and that's 2 carbons fewer than heptane, because these numbers, 2.2.1, refer to every carbon in this structure except for the bridgeheads. So these 2.2.1s are going to always equal 2 less than the total number of carbons present. And then we prefix it with bicyclo. Now, generally speaking, the numbers are arranged from highest to lowest, and that usually just allows us to draw the molecule in the easiest way possible. It's much easier to draw a molecule with a 1 carbon bridge than a 2 carbon bridge, but you could kind of view this as having 2 carbons on one side of the bridge, 1 carbon on the other side of the bridge, and then a 2 carbon bridge. See that? It's kind of like a 5-membered ring, 2 plus the bridgeheads plus 1, and then a 2 carbon bridge. Whether you think of this as a 2.2.1 or a 2.1.2 or a 1.2.2, no matter how you view it or draw it, it's going to be the same structure. So just kind of out of convention, we start with the largest numbers on the sides of the bridge and have the smallest numbers between the bridge. If we can take that pattern, we can apply it to a fused bicyclic. What would this be? First of all, let's identify our bridgehead carbons. What carbons share the 2 rings? Well, it's these guys right here, right there and right there. Those are our bridgeheads. Only in the fused case, there are no carbons between the bridge. So we have 4 carbons on one side, 1, 2, 3, 4. 4 carbons on one side of the bridge. 4 carbons on one side of the bridgeheads. 4 carbons on the other side, 1, 2, 3, 4. And then 0 carbons between the bridge. So this is a bicyclo 4.4.0 decane. Decane because it's 10 carbons total. 4 on one side, 4 on the other. That's the 4.4 plus the 2 bridgeheads, which we don't count in these dots. So bicyclo 4.4.0 decane. A dot 0 in our brackets always will refer to a fused bicyclic. That's a clue. If you see 4.4.0 or something silly like 0.4.4 or 4.0.4, a dot 0 will always mean a fused bicyclic because there are 0 carbons between our bridgeheads. If there's a non-zero number between the dots, that means that we've got a bridged bicyclic. And then look at spiro. Spiro is a little bit different. We don't need 3 digits between here. In a spiro, there is no bridge. There is no bridgehead. There's just that single kind of spirally carbon, the carbon that's shared between the 2 rings. So what do the 4 and the dot 4.4 mean? Well, that's 4 carbons on one side of that central point and 4 carbons on the other side of that central point. So we've got 4 on one side, 4 on the other, plus that central point means that we've got 9 carbons total, so it's nonane. So spiro 4.4 nonane would be how we would name the spirocyclic molecule. Having 2 digits in the brackets instead of 3 implies that it is a spirocyclic molecule. We just put spiro there for extra clarification. Again, here's kind of the annotation, how we arrive at 4 carbons on one side, 2 carbons on the other, 0 carbons in the middle, 4.2.0. That's a fused bicyclic because it's got the dot 0. Here's something where we've got 3 on one side, it's over here, 2 on the other side, that's over here, 1 in between the bridge, so 3.2.1, that's 6 carbons, plus the 2 that are on the bridge themselves, the bridgeheads, means that this is octane. And again, there's no dot 0, so this is a bicyclic, a bridged bicyclic. Now, there's a special rule that accompanies bicyclic molecules, and that is Brett's rule. Brett's rule says that a bridged bicyclic compound cannot have a double bond at a bridgehead position unless one of the rings contains at least 8 carbon atoms. So, again, these are bridgeheads. We are not allowed to have double bonds on those carbons. Here's why. Here's a structure where we just did that. We've got a bridged bicyclic molecule. Our bridgehead carbons are carbon 1 and carbon 4 here as numbered. And we've got a double bond there. Well, that looks fine. We put a double bond there, great. What's wrong with that? Well, the problem is that when you have a double bond on a bridgehead carbon, notice that we have a trans double bond in a 6-membered ring. Where's the trans double bond? It follows the blue pathway from 3 to 2 to 1 to 6. That is a trans double bond. See that? It's like a zigzag. 3 is up, and then 2 to 1, and then 6 is down. You cannot have a trans double bond in a 6-membered ring. It does not work. I dare you to draw it. Go draw a cyclohexane ring and put a double bond on it. It will be cis. You are allowed to have a cis double bond in a 6-membered ring. You're not allowed to have a trans double bond in a 6-membered ring. Doesn't work. There's not enough carbons to make room for that trans double bond. So even though it looks okay when you draw it this way, be aware that you are violating a rule. That's Brett's rule. So why is it that case that you can have a double bond on a bridgehead carbon if one of the rings contains at least 8 carbon atoms? Like in this case, here we've got a bridged bicyclic molecule. Our bridgehead carbons are carbon 1 and carbon 6 as drawn here. Notice that we've got a double bond on the bridgehead, but the blue ring is 8. So again, the trans double bond is in the blue ring. From 8 to 1 to 2 to 3, that's a trans double bond. It's kind of zigzagging. It's not going in a U shape like the cis does going up to the bridge here. So there's a trans double bond in our blue 8-membered ring, but that's okay. There are enough carbons in an 8-membered ring that a trans double bond will fit. Go back and look at our drawings of cyclooctatetraene from our conjugated systems chapter. I showed you that there is a form of cyclooctatetraene that has all cis double bonds, and there's a form of cyclooctatetraene that has 2 cis double bonds and 2 trans double bonds. That's allowed. If you can have 8-membered ring with trans double bonds, so Brett's rule allows for that, but it does not allow for trans double bonds in any rings fewer than 8. So be aware of that. You're not allowed to do that. That means that if you've got a ring like this, you're not allowed to do elimination at that site. Even if you've got a leaving group adjacent to a hydrogen, if doing that elimination would put a double bond on a bridgehead carbon where one of the rings is fewer than 8 carbons, you are violating Brett's rule. You will not be able to do that reaction. It will not work. Okay, just a reminder, we did E1 and E2 as the methods to synthesize alkenes. You take a leaving group and an adjacent hydrogen with a strong base that's big and bulky, making it a weak nucleophile. You grab the H, electrons fall in, push off the leaving group, we make the pi bond, and you can get E or Z or maybe one or the other. The technical name for an E1 or E2 elimination is dehydrohalogenation. You are losing a hydrogen and a halogen. So we call that reaction dehydrohalogenation. Remember that E1 and E2, dehydrohalogenation, follows Zaitsev's rule. If we have the choice of making a monosubstituted alkene, or I guess in this case it's a di-substituted, we've got the ethyl group on the double bond and a methyl group on the double bond. That's di-substituted, the hydrogens don't count. Here we've got tri-substituted, methyl on the double bond there, two methyls on the double bond there. So tri-substituted versus di-substituted. Zaitsev is the more substituted, so it's going to be the more favored product. This is formed in about 71%, about 70-30, Zaitsev to Hoffman. Remember, we call this Hoffman because there's another reaction that actually gets you the Hoffman as the major product. We call that Hoffman elimination. It involves amines, and so we're going to talk about it in chapter 19 in the second half of this course. Now, your book shows you this, and this can be a little bit misleading, so I really want to clarify it. Here they're showing, notice that in the top reaction, we're using ethoxide, a 2-carbon alkoxide base. That's a strong base that's not particularly bulky. Here they're using T-butoxide, and they're showing you that if you use a bigger, bulkier base, you actually get Hoffman product as the major product. The reason why they're saying that happens is because if your big and bulky base can't reach the Zaitsev hydrogens because they're so hindered by the other groups around them, they're more likely to grab the less substituted hydrogens and get you the less substituted alkene. That might be the case, but only when you have tertiary leaving groups and a super bulky base. So just be aware of that. Usually I'm fine if you always pick the Zaitsev product as your major product. In the case of a tertiary leaving group, notice that this bromine is tertiary. It's on a carbon with 1, 2, 3 other carbons. That means that the adjacent hydrogens are going to be fairly blocked. And that big bulky base won't be able to grab the more substituted ones, so you won't get the more substituted double bond. Just be aware of that. If you want to be super picky, you can follow that. What's going on there is that if you have a less bulky base, the tertiary is slightly slightly more inaccessible than the secondary. And if we increase the bulkier base, we're going to decrease the ability or increase the inaccessibility of the tertiary, and we're going to do it to a certain point where they cross some threshold of being no longer accessible. With a less bulky base, you can grab both, but you're always going to grab the tertiary because it gets you the more substituted double bond. If you have the bulkier base, these things become less accessible and the tertiary becomes inaccessible completely. So your only option is the secondary. We also looked at dehydration. That was, remember, a special example of E1 and E2. We don't call it dehydrohalogenation because we're not losing a hydrogen and a halogen. Instead, we're losing a hydrogen and an OH. We're losing HOH, which is water. So we call that dehydration. We went over that fairly thoroughly in the E1, E2 chapter. I want to show you one more reaction that involves elimination of what we call vicinal dibromides. This term vicinal refers to the relative position of two groups on a structure. Here we have two structures where we've got two bromines. When the two bromines are on the same carbon, we call them geminal. And these could be any groups. These could be OHs, they could be bromines, they could be chlorines, they could be fluorines. They really could be any groups. I'm just using bromines because bromine in particular reacts in this context. I'm going to show you on the next slide. But if the two groups are on the same carbon, we call them geminal. That comes from the Greek, or I think it's Latin. I don't know, Greek or Latin. Look that up for extra credit. Gemini means twins. So these guys are twins, geminal. If they are on neighboring carbons, we call them vicinal. Think like vicinity. They're in the vicinity of one another. They're neighbors. So there's a specific type of E2 mechanism, an E2 reaction, that involves elimination of vicinal dibromides. Here's how it works. Here's our vicinal dibromides. Our reactions are potassium iodide, Ki, and acetone is a great solvent for this reaction. And what we get is a double bond. Notice that we have eliminated both bromines. We didn't eliminate an H and a Br. This is not a normal dehydrohalogenation. It is an E2 mechanism, but it's not dehydrohalogenation. Make sure you understand that distinction. Here's how it works. It turns out that iodide and bromide make fairly strong bonds with one another. So here we have potassium iodide. The book actually uses sodium iodide. Either way, the sodium is just a bystander. The potassium is just a bystander, a spectator ion, we call it. But the iodide kind of acts as a base in the context of, say, dehydrohalogenation. The iodide grabs a bromide, makes that strong bond. That causes bromine to release its existing bond. Again, remember, iodide feeds into the antibonding orbital of the bromide. That causes the corresponding bond to break. Those electrons fall in to the antibonding orbital of the carbon-bromine bond. That causes the carbon-bromine bond to break. Bromide leaves. Look at what we get. We make a double bond. It looks just like elimination, but we did it by making IBr, iodine bromide, and Br minus. Again, it's not dehydrohalogenation because we're not using a base to remove an H and an adjacent halogen. We are using Ki to remove vicinal dibromides, but the mechanism is E2. The mechanism is exactly the same as the E2 dehydrohalogenations that we looked at. I'm going to show you a very cool example of a reaction using this mechanism, and we're going to wrap in a lot of the prior contexts that we've talked about for, let's say, Newman projections, chair conformations, E2 mechanisms, elimination of vicinal dibromides, formation of double bonds, Brett's rule. We can incorporate everything that we know in one reaction. It's very cool. We're going to do that in a workshop. So that's the end of lecture 10. The workshop section from Stramanis that covers this material is Chem Activity 6, Part C. Make sure that you keep track of your reactions. Okay? Make flashcards or make a list of reactions or make a reaction map. Stay organized. Don't fall behind. Don't get lost. Good luck.